Good morning and welcome to Discrete Mathematics. So why don't we do some of that math stuff. Let me get the correct color. And we are okay there. So today this is actually the very last section in the book. You're all done after this. So this is chapter 10.7. And the title of this is called Spanning Trees, and Shortest Paths. But you're going to like this. We're not even going to talk about spanning trees. You can go ahead and read it, but we won't cover these. They are kind of interesting. And in fact, what's going to happen here, we are going to talk about finding the shortest path. And in the book, they talk about what's called Dijkstra's algorithm. Dijkstra is a very famous man. But I think this algorithm's a little complicated, so we're going to come up with our own. We're going to come up with something that I think is a bit easier. If you want to use Dijkstra's algorithm, you're certainly welcome to. But for the first time in this chapter now, we are going to be considering weighted graphs. And what I want to do here is I'm going to draw a graph for you. I'm going to call this point A, and we're going to come up here to B, and we can come down here to C. And what's going to happen is we're going to associate some numbers with these edges, and we'll talk in a moment about what that could mean. And now from B, we're going to come way over here. We'll have another vertex called D, 6, and we'll have this come all the way over to E, 6. We'll have this go from here down to here, 5, 2, and over here is a vertex that we'll call Z, Z. Do Namibians say Z or Z? Americans say Z, Canadians say Z. 12. Okay, so this is a weighted graph. Okay, so each one between any 2 points we have an edge, and on an edge there's a number associated. Now what could this possibly mean? There are lots of interpretations to this. This could mean distance. So it could mean that from point A to point B is 3 kilometers. It could mean from point A to point C is 4 kilometers. That would be one interpretation of this. Another interpretation of this is you could think of perhaps this is a network, and maybe these are all of the vertices represent routers or switches, and maybe the numbers on the connections between them represent the network traffic. Maybe this represents that at this time there might be 3,000 packets on the network between A and B, and there are 4,000 packets on the network between A and C. So there are a great many different interpretations that you can attach to this. But here's what we want to consider now. And again, you could think about this either you're driving in your automobile, or you could think of yourself as a network packet. Maybe you're at point A and you want to go to Z. And you ask the question, what is the shortest path from A to Z? Okay? Now, I do have to give you a little bit of a warning here. The algorithm's easy. Don't worry about that. This picture that you see right here, I took out of this is page 712 in the book. And something very, very interesting happens if you look at page 712 in the book, if you look at this diagram, they find the shortest path from A to Z, and they do it through successive steps. And when they originally draw this graph down here, when they go down to step 1, all of a sudden the distance between C and E changed, and it went from 6 down to 1. And that completely changes the answer. So this is a misprint in the book, if you're following closely, which I hope you are. Anyway, we're going to solve this thing, and we are not going to use Dijkstra's algorithm. We are going to use another algorithm that's referred to as branch and bound. And the reason why we're going to do it is because it's easy. And I know we all like easy. So here is what we're going to do. I'm going to move this window over, and we're going to get another. We're going to bring this over here. So remember, we're starting over here at A. And here's the idea. If I'm in A, I can go to B, or I can go to C. And if I go to B, it's going to cost me 3. And if I go to C, this is going to cost me 4. So that when I get over here, I'm going to say I have a total cost of 3. And if I come over here, I have a total cost of 4. Now, what I'm going to do at this point is I am going to expand the node that has the least price on it. Now, out of these two here, B has the least price on it, or it's the least cost. And we can see, I could go back to A, but that would be really silly. But from B, I can go to D. And if I go to D, it's 6. And the total cost would be 6 plus 3 is 9. From B, I could also go to E. And from B to E is 5. And that gives me a total cost of 8. So I've now expanded B. And now, again, I look at all of what I refer to as the terminal nodes. I look at the nodes at the bottom of the tree here, okay, and I notice the one that has the least cost on it now is C4. So what I'm going to do is I'm going to expand C. Now, if I expand C, C can only go to one place, and I take this down to E, and that has a cost of 6. So when I get here, it's 10. Okay, now I notice a couple of things here, and again, I'm looking at the terminal nodes, and I notice here's a way to get to E that only cost 8. Here's a way to get to E that costs 10. I don't even need to consider this part of the tree anymore. Okay, if the answer includes going through E, I have found a cheaper way to do it already. So now I'm coming over here, and I look at the cheapest nodes here, and I go, okay, I'm going to expand them. So from E, I can go to D. And if I go to D, it's got a cost of 2. And from E, I can also go to Z. And it can cost 12. And if I take E down to D, I add 2 to 8, and I now get 10. And if I go from E to Z, I get to Z, and it's now 20. Now, at this point, I might get very excited. And I go, well, I have found a way to get from A to Z. But the point is the following. I have a node that is still less expensive than 20. First of all, notice over here I have D9 and D10. Okay, so I have found a cheaper way to get to D by going this way than coming down this way. So I can certainly get rid of this. I don't need to count that. But over here, I still have a node. I have a partial TOR that is less expensive than this that got me to my destination. So there may be a solution coming down this way that's going to be cheaper than that. And sure enough, that turns out to be the case. Because from D, I can either go to E, which has a cost of 2, which would make this 11, or from D, I can go to Z, and here that has a cost of 7, and I have found 16. And the thing that I note over here is that 16 is less than this one here. So now this is the one to consider. Okay. Now, in theory, I am still not done. And the reason why I'm not done is because I still have a torr over here, which is of length 11, that is less than this over here. But I do note the following. I've already found the torr up here that didn't lead to the optimal torr, where E was 8, and here E is 11, so we know that this can't be it either. And this is my solution right here. So the torr, the cheapest way to get there is to go from A to B to D to Z, and the cost of it is 16. And that is the solution. The key point here to remember is that you're not done if you just get to the destination. If you get to the destination and there are still partial torrs that are less than the cost of this one, you have to keep expanding them. You're only done when all of the terminal nodes down here have torrs on them, all the live ones, the ones that we haven't eliminated. They have to have a length that is greater than that. Then we have indeed found the minimal torr. And that, my friends, is the branch and bound okay, and it finds the minimal torr, the minimum cost. The minimum cost path. I told you, easy.